Okay, thanks. Sorry for this uh, waiting. So, the purpose of this first lecture is to give you an overview of the needs that we have to take into consideration when we build a double beta decay experiment. And okay, more or less, this is what you can call the menu when you have to prepare this, build this experiment, or if you prepare, if the, maybe better to say to design this experiment. And you have a list of choices, requirements, or general needs that you have to analyze in order to design your experiment. And this is not a hierarchical list. That means you can reshuffle most of these points, and they are correlated one with the other. And what I have in mind for this lecture is to go through all these different points and try to discuss with you and together understand what are the main choices in the experiments that are presently running and what are the motivation for these choices. So it's like an exercise in which we try to define our own experiment starting from scratch. And before that, you have to be aware that maybe that is our life as experimentalist, that is like the goose game, and in some of this step we will find a showstopper, and then we have to go back and design again your experiment. Now it is not like that, because we have tens of years of experience in building a double beta decay experiment, and the new generation of double beta experiment is based on a lot of demonstrators and middle-size experiments that have already been operated. So we have a lot of experience, and we already have found a solution for most of these points. So let me start from to give you few information on what we need to know before designing an experiment. Therefore, what we want to look for is that process in which you have a spontaneous transition of a nucleus with the emission of 2 electrons. And this is very similar to the well-known beta decay. Is a second order transition, we say, because you emit 2 electrons, and for sure it is possible in this channel that we call 2 neutrino double beta decay. And this is the Feynman diagram. And what we are interested in is the channel in which the 2 neutrinos are not emitted. This is the transition, or if you prefer, it's Feynman diagram, and we call it neutrinoless double beta decay. So we have to design an experiment that is able to detect this transition, being aware that this transition does exist. And from the theoretical point of view, we have a connection between the half-life for the neutrinoless transition, but also for the 2 neutrino for sure, with, in the case of the neutrinoless transition, with a parameter that we call Majorana mass, that is, is expressed here, is a sum over the free mass eigenstates, the one that Claudia introduced this morning. The free mass eigenstates that are weighted with the elements of the mixing matrix written in for assuming that the neutrino is a Majorana particle. You will see more from this point of view in Claudia lectures. So just take it, this is, I mean, the parameter that is in what we call the beyond standard model physics, because assumes that neutrino is a Majorana particle. It's not exactly the mass of neutrino, but is a way to evaluate masses, and we call it Majorana mass. And the half-life, the inverse of the half-life, is proportional to the square of this parameter. And here you have, as in all the nuclear decays, we have two factors. One is the phase space, and the other is the nuclear matrix element. So again, if we look at the present picture of neutrino masses, you have already seen this plot in Claudia's slides. We know from the oscillation experiment that at least two neutrinos are massive, because we measure two differences in the square masses. Okay, this is an experimental observation. We see neutrino oscillation, and the only way from the phenomenological point of view in which we are able to describe them is that neutrinos have mass eigenstates that are different from flavor eigenstates, and we have these two different pictures for this, for the ordering of these mass eigenstates. We can have two mass eigenstates that are quite close together, but also they are the lighters, with one more splitted mass eigenstate here, and the reverse. From the point of view of what I want to introduce you is the relationship between this Majorana mass parameter and this free mass eigenstates that is given by this, this relation, and that you can rewrite in a way to, to use the difference, the measured differences in mass eigenstates that are these two, and the parameters of the PMNS matrix that are here. So the idea is the following. We have a Majorana mass eigenstates, Majorana mass parameter that is given by this relationship. Here you have three parameters, the mass eigenstates, and we know their differences. They are square differences. So we can rewrite this relation on a different basis. And this just to come to this plot that I will use. This plot shows us the relationship between the mass, the Majorana mass, and the lightest of the free mass eigenstates. It can be as low as 0. And given what we know from oscillation experiments about the mixing parameters, mixing angles, and the two Majorana phases, we know that we have this, possibilities for the Majorana mass. It can lay somewhere in this gray band or in this red band. And why I'm telling you this now that I want to discuss requirements. You will see all this, phenomenological discussion in detail with Claudia, but I want just to provide you one important information. what is the value that our experiment has to explore. This is an important point because it sets, I mean, the value of the half-life that I need to be sensitive to. And today, all experiments have more or less explored the region that is in the top higher part of the gray band, or they are starting investigating something in here. And the goal of our future experiment will be to fully explore this gray band that has a name, is the inverted hierarchy or inverted order band. So just your takeaway from this discussion is that just that this parameter that I want to be sensitive to has a value of about 20 electron volt. This is my goal. Milli electron volt, sorry. And this I skip. So there are other input that can be important because I gave you I mean, the goal that we have on this parameter. We need to know also the values of these two. This come from the theory. The phase space is something that can be evaluated quite easily. And here you see the different values for a number of candidates to double beta decay. And more or less it scales with the fifth power of the Q value of the decay. So you know what is the Q value, is the transition energy, I mean, is the energy that is available for the decay products, and it comes from the difference between the mass of the decaying nucleus and the sum of masses of the products. So just to show you that it scales with the Q value, you can compare the same nucleus. There are two isotopes of tellurium. Both are candidates to double beta decay. One has a very small Q value, is tellurium 128, and the other is tellurium 130, and you see that phase space changes a lot. Yeah. Sorry, which? Yeah, I go back here. No, this one. Okay, it's just because it's difficult. I mean, let me say like this. We want to explore the full range, of course, but we proceed step by step. And the present experiment were able to achieve more or less a sensitivity that is here. And the goal of the next generation experiment is to be able to go down here. And being able to achieve a sensitivity that is in here is extremely challenging. So at present, it's very, very difficult to think that to go beyond this level. And I mean, this is one of the points that we want to understand better in this lecture. Okay. Okay, the phase space is, I mean, what you always have in when you evaluate a half-life due to nuclear decays. Okay, I come here. So these are all candidates to double beta decay. Just take it, we go back to this concept of candidates in a while. Okay, so it's just because this is a plot that you can find in literature, and already is a selection of possible candidates. My point is just to give you some information on this relationship. Here is something that establishes our goal, and our goal today is like 20 millielectron volt. This is a number that we are able to evaluate, and the important takeaway here is that this number increases with the transition energy of the nucleus that you decide to study. And you see, what is the point? If you want to look for a decay, you want to be able to see this decay, to see events that correspond to this decay. And what we will see is that this half-life is extremely long. And therefore, you would like to choose a candidate that gives you some chance of seeing the decay. And so here you already see one of the possible requirements for candidates. If they have a high transition energy, then they have also a very good phase space. That is why I study double beta decay in tellurium 130. I do not study this. I mean, it's a byproduct of experiments, but I have no chances of seeing this in the neutrinoless channel. I mean, the third ingredient in the half-life is the matrix element. You will have lectures from Luigi Coraggio on this topic, and this is the nightmare of the experimentalist, because here you have to rely on nuclear models, and nuclear models have kind of flavor. They have, you have different kind of models, and within the same models, these are all I mean, names that identify different models. For each of them, you have different flavors depending on the approximation that are introduced. And at the end, you get a number of different predictions for this transition, nuclear matrix element. What I must say is that when I was a PhD student, this range was much higher, at least one order or even more of magnitude higher. So now people that have my experience, I mean, as old as I am, are very glad to see that the spread now is a factor 2 or 3. And you see the problem from the point of view of an experimentalist. If I have to design an experiment to measure this half-life, I need to understand which is the order of magnitude of this half-life. And it is true that I do not have information, direct information on this. I can make some guess, and now I have information at least from oscillation. When I started working in double beta decay, oscillation was not yet discovered. And so we really did not have information. No, the spread depends on the spread. So let me, it's something that we will see in more detail. The spread on the result, let me say like this. What you measure directly is the half-life, okay? And I assume, but Claudia can confirm, once I see the decay, that's enough to claim that the neutrino is a Majorana particle. I mean, you have to be pretty sure that that is the decay, and we will see the signature of this decay. But once you have seen that the decay does exist, you can say, okay, neutrino is a Majorana particle. Then you have to convert your signature into a Majorana mass. Of course, you are able to convert with a very high accuracy the events that you have seen in your spectrum in a half-life. The half-life is just the number of events divided by the time, the exposure time, the time in which you have observed them. But then you have to convert, and in order to convert, you need to have this number, and you don't have. And so the pragmatic solution that have been adopted by all experiments is to use a range. Okay, I can say the Majorana mass, so I have a number here, and once I invert, maybe I have a slide here. No, okay, it's somewhere else. But when I convert this number into Majorana mass, I will quote a range. So you open a paper and you see the half-life is longer than 10 to 26 years, and the Majorana mass range is between 100 and 300 millielectron volt. That is there is a second point in which it's important to be able to convert into Majorana mass. When I want to compare experiments that are studying different isotope, I'm not. It has no meaning to compare the half-life. I need to compare this parameter, and then I have to find a solution for the uncertainty that, or the spread that I have on the nuclear matrix elements. But we will go back to these topics later. So let me, yeah. You have to speak low. No, the phase space has no spread. I mean, there are small, very, very small changes depending on maybe on approximation and so on, but it's, I mean, it's easy to be evaluated. The problem is the nuclear matrix element. The problem is that we do not have the standard model of nuclear physics. So nuclear physics is completely different from what we are used in particle physics. And you still have different models, and each model is able to describe only, not completely, all the phenomenology that you are able to observe. But Luigi will discuss this point. So let me go back to my list. So just start from this first point, and let me, okay, remind that our goal is we want to study this decay. Okay, this is the decay we want to study, and the channel in which we are interested is the one without neutrinos, but keep in mind that we have also the possibility of emitting two neutrinos. And I focus here on double beta decay with the emission of two electrons, but you can have also double capture or the mixed emission of capture and the beta pu emission, or two positron emission. So you have all the channels. So the point is how can I choose candidates in the table of isotope. Which are the good candidates? Which are the candidates and which are the good candidates? Where I can start to look for candidates. Have you any suggestion? This is a problem of nuclear instability. Exactly. Exactly. No, yeah, that is already the solution. But I mean, the principle is I need to find, I mean, this isotope has to be lighter than this one, basically. Now, there is a second condition that we want to fulfill, is that we want to select isotopes. You see here, I wrote the conditions for the double beta minus decay and double beta plus decay, and it's not exactly this, but no, okay, is this with greater than, and I have also a second condition that I want to be able to fulfill, is that I want to select an isotope that is stable but for double beta decay. Why this? Because this is a second order transition. If my candidate has a different, I mean, the possibility of decaying with a larger amplitude, what I will have is that I will have, I mean, two channels to control and maybe one much faster decay channel than double beta decay. So it's much better if I have to look only for double beta decay. And so the solution is quite simple. I can write the formula for the binding energy as suggested by one of your colleagues. And if I look at this, this is what is called the Weizsäcker formula. And I look at the shape of the binding energies for different values of the atomic number and the nuclear mass. I discover that I can draw these two parabolas that are rise from this term, that is the pairing term. And what I see is that for isotopes that have an even number of proton and of neutrons, they lay on this lower parabola, and they have a forbidden beta decay, so they can't be unstable for beta decay, but they can achieve, I mean, reach a lower energy level by two beta decays, so with a double beta decay. So these are among nuclei that have that we call even. We have a bunch of isotopes that are stable for beta decay, but unstable for double beta decay. And of course, there is a further instability that here is not considered, that is alpha instability, but we will see. Okay, so this is the solution, and but there is a much clever way to find this solution. You open the web and look at Wikipedia, and you find all the list of the. I don't know if it is correct. I discovered this a few days ago that it was there. But I must say that when we started, the browser did not exist, and even internet did not exist. So here you have a very good list. In this list, these are isotopes that undergo double beta minus decay and this double electron capture. And the red isotopes are, I think, those for which the 2 neutrino double beta decay have been observed. So the standard model allowed channel have been observed. So you see the problem. The list is quite long. I need some criteria to choose my candidate. And okay, on Wikipedia you also find, it's not completely up to date, but you also find the table of the 2 neutrino half-life measurements. And you see that, I mean, the unit is 10 to the 21 years. That is quite long. I mean, it's important because it means that you have to wait for a long time to see a decay. And keep in mind that this is expected to be much shorter than the neutrinoless double beta decay. So here, two possible criteria to choose your candidate. On one hand, you have the transition energy or Q value. I already have told you that when, I mean, if Q value is high, I expect to have a shorter half-life. That is something I'd like to have. There is, here you see already a selection of isotopes, and what I have done, and Wikipedia did not do, is to select isotopes with high Q value. Maybe they are not all of them. Those with high Q value are beta minus decays. So these all isotope decay with the emission of 2 electrons, negative electrons. And here you see the Q value. There is another point that now I just quote in general terms. We will go back later. In general, it is better to look for decays that have a higher Q value, because also the signal that we will have to be able to find will be more clear in your data if the energy, the total energy, is higher. And this is why from Wikipedia we have extracted, I mean, the experimentalist community has extracted these isotopes. And on the other side, this plot is shows you the isotopic abundance of these nuclei. So the point is the following. I have to measure a very rare decay, and therefore I will need a lot of nuclei in my source, and it's important that I do not have inert material in my source that doesn't partake in my experiment. And you see that most of these isotopes have a very low isotopic abundance. The only exception is tellurium-130. What can I do? Well, in principle, of course, I can still use natural isotopes and accept that only 10% of my source will be active. However, this is not a good solution, and we will see later on why. And so there is another solution that is enrichment. What is the problem of enrichment? There are two problems, you can guess. Cost is a huge problem. Any other? Sorry, say it again. Usually not. And usually enrichment, since it selects A, the mass of your isotope, generally does not add contamination, but removes contaminations. The other problem is that not all the isotopes can be enriched. I mean, there is only one technique to enrich materials that is based on the centrifugation of, the natural material. And again, you can take it from Wikipedia, and allows to select the mass of the isotope that you are interested in. And this technique can be applied only if you are able to produce your isotope in the form of a gas. So you need a molecule that contains your isotope that is a gas. And generally, this is an hexafluoride that is highly reactive and corrosive, as all fluoride. So handling this is not easy. And centrifugation is a very inefficient way of extracting enriching material. And so you have a single step is not enough, and you have these devices work in series, and you have an inlet and an outlet where you extract enriched material, but this enrichment in one single stage is not so relevant. Keep in mind that we start, in our case, from 10%, and we would like to achieve 95%, something like that. So you have a series of centrifuges, and the outlet of the first goes to the inlet of the second and following. And this is extremely expensive. But it doesn't work for all the isotopes. And the one that is well known that can't be enriched is calcium. And so with calcium there have been experiments, double beta decay experiment done using natural material many years ago, but now is not used anymore. Okay, and this industry is an industry that is not, due to the problem of this technology is strictly connected to nuclear proliferation, and therefore, there are few places in the world where it is possible to do enrichment, at least mass enrichment. Of course, there are a lot of plants that are used to produce the fuel of enrichment plants. Of course, you do not want to, I mean, so enrichment power reactors. You do not want to use the same devices for your isotope, because really in that case you will add a lot of contaminations. But generally, the plants are different, and also the design and the way in which this devices is operated depends on the how light is the, depends on the mass of the isotope that you have to enrich. Okay, so again on the source therefore is, the amount of candidates that I want to put in my experiment. So the question is, how large must be the source for my future experiment? And the other question is, how long do you want to wait to see a decay? 1 year, 10 years, 100 years. Now we quote sensitivity of the experiment on the basis of 10 years, okay? And the reason is that the decay is rare and we are not able to use such big sources to be able to see tens of decays a year. Okay, let's do this exercise. If you have 1 mole, let's take germanium 76 as our candidate. And now we know that the half-life, let's say the half-life is larger than 10 to the 26. What is the rate? Okay, the rate is the number of double beta decay candidate divided by the, we can use even the half-life or the lifetime of the isotope. How many atoms do I have in 1 mole, and what is the weight of 1 mole? And this is yeah, and this is the weight of 1 mole, right? So this is in years. So you have 10 to the minus 3 decay in 1 year in 100 gram, more or less. So you understand that if you really want to be able to see some decay, you need a source with the size of 1 ton. Of course, now, this is an exercise done on the basis of the results we got, we have now on germanium. Depending on the isotope, it can be a bit less than 1 ton or something more, but this is the size of the experiment, or the size of the source that we have to buy. And if you want to, coming back to what I've shown you before, if my goal is here, now this plot was prepared for this mass. My expectation, considering the spread of the nuclear matrix element are here for the different isotopes. So you see they are between 10 to the 27 and 10 to the 28, depending on the isotope. And here I have selected the isotope that have been studied in the recent years with good sensitivity. Okay, so if we want to understand how challenging it is to study searching this decay in 1 ton of with a 1 ton source, we need to understand how we can look for this decay. So the question is, can you identify the main experimental signature? Because this is what I have to do to design an experiment, understand what I have to measure. So come back to this transition. And assume that we choose a candidate that have a transition energy of the order of 2 MeV, just to fix ideas. And what can we use to look for this transition? Can we look at, this is the daughter nucleus. What's the energy of the daughter nucleus in this decay, more or less? Yeah. So do you know cases in which we are able to measure a nuclear recoil? Sorry? Yes, in neutron scattering, we measure a nuclear recoil. When you have fast neutrons, they scatter on nuclei and they produce nuclear recoils. Okay? And we are able to measure them. There is also, a branch of astroparticle physics that looks for nuclear recoils. It is, something similar to what a neutron can do, but is produced by a different particle that we look for, is WIMPs, okay? We look for a kind of dark matter. Dark matter have a lot of candidates, but one of the candidates are WIMPs, the weakly interacting particles, and we assume that they interact with matter more or less as a fast neutron. The only difference is, the energy that, and so in that case, we are able to measure nuclear recoils. Excluding one experiment, we have never seen an indication of WIMPs-induced events, but we look in what energy range of the spectrum. We look for a nuclear recoil with, yes, about in the range of 110 kiloelectron volts. Below, we are even not sensitive because no detector is able to look for them. And there is only, the from the point of view of technology, not all, you really have to develop dedicated detectors able to look for these events. So a WIMP with a mass of order of JeV is able to produce a recoil of 10 kV. But in a decay, can we detect recoils in some decay, nuclear recoils in some decay? There is which is the decay where you have the larger energy in the nucleus, in the recoiling nucleus, alpha. And what's the energy of, I mean, if you look at alphas produced in nuclear radioactivity, in natural radioactivity, do you know what is the energy of the recoil? 100 of kevs. Is 100 of kevs. So I mean, the prototype is very similar, but here you have an alpha particle and you have 100 of keV. Okay. And so here, the amount of energy is much smaller. And it's by far smaller than what we have ever measured. So we will never be able, I think, to measure a recoil. So any other possibility to identify this? Yeah, exactly. So in principle, you could, I mean, is a different chemical species. So in principle, you can devise some technique to identify these different atoms. And if I go back here, okay. So in these two measurements you see of the two neutrino, this and the other. Okay, here. Okay, here is the. Okay, when I started working in double beta decay for both these two isotopes, we had a half-life measured with a geochemical method. And the technique is the following. It was, I mean, they look at two rocks that contained tellurium. Tellurium decays in xenon, and so they searched for xenon atoms inside the rock. They counted the number of xenon atoms, and they were able to evaluate the half-life. It was an inclusive half-life because, of course, with this technique, you are not able to distinguish between two neutrino and a neutrinoless decay, but that was a technique. Basically, of course, there were some disagreement in literature because xenon is a gas, and so you have to be sure that it was not able to escape from the rock, so it's not exactly a measurement. Sorry? Yeah. Yes. Well, you see, of course, it was not within the error. It was, at that time, it was really discussed a lot, this disagreement. And I think there was also on tellurium 130. Now there is an experimental measurement, so you do not see it reported. But I remember that in the first, when we started working with tellurium, when we wrote the papers, we always were quoting these results that were controversial and so on. But this just to tell you that it's possible to, I mean, in some way it is possible to identify the daughter, but in a real experiment is still to come. Okay, so we have to rely on the two electrons. What is the signature of these two electrons? What we have discovered now is that most of this energy goes to the electrons, okay? And this is completely negligible. Therefore, all the energy is here. That means this is, yes, the distribution is, okay, if I, if I write here this, which kind of energy? Yes, but this energy, what is the energy of what? Is the sum energy of the two electrons, okay? So in my neutrinoless is a peak, and if I have two neutrino here, it is something like that, okay? And the reason is that when I have this in the neutrinoless channel, the two electrons, I mean, if I look at two electrons as a single particle, this is a decay with the emission of only two particles, and so there is a clear sharing of the energy. And while if I look separately to the two electrons, I have a spectrum. Okay, one more question before we go ahead. What happens when these electrons travel into matter? Okay, keep in mind, this is my source, and this is 1 ton. And here I have a double beta decay. What happens? I emit two electrons. Do they escape from my source? What is their range? Well, depends on the, say it's something is, let's consider a solid with average density 3, 4, like something like that. It's millimeters. And so here I have 1 ton of material, and how can I detect these two electrons that do not come out from the source? Well, in general, I mean, the principle is that I need that the source is also the detector. So whatever these two electrons do, they can produce ionization hits or whatever. I need to be able to detect them when they are inside the source. You understand? It's the only, there is a different solution that was adopted times ago, and still we have one experiment, but it's difficult to scale in mass. You can use a very thin foil, so thin that the electrons go out from the foil, and then you detect them in some way. It could be, in that case, it was a TPC. It was the NEMO-free experiment. But you understand that I have to fill my gas detector with a lot of foils, and each foil has to be very thin, and consider that, I mean, what happens to my signal if the foil is not thin is that I start to see a tail in this peak, and the tail becomes longer and bigger as soon as the foil is thicker. And then so the clear signature that I like very much, that is a monochromatic peak, becomes something that is not exactly a signature, and I can have a lot of other events that can mimic a signal like this. And so this is not something that I like. Okay, so I reported in the slide you find a range. I don't remember in which material, but it's the range of, no, it's a range normalized to the density. I think it was silicon or something like that, but a range of electrons, just to give you an idea. Okay, so this is our spectrum. This is how we generally show the spectrum. And now we are ready for the next topic, that is, or the next problem that we have to solve before being able to design our experiment, is to understand which kind of events can mimic a double beta decay. So the problem is that once you have transformed this 1 ton source into a 1 ton source is called detector, you discover that life is not so nice, because you were very glad of this monochromatic signal, and then you have to face 2 problems. The first one is this. So this is this monochromatic signal generally is shaped as a Gaussian to represent the energy resolution, whatever detector you are choosing. So you will not, even if, I mean, the energy is really the transition energy, because the recoil energy is completely negligible. And you know what is the accuracy with which I'm able to measure this? I mean, it depends on the accuracy with which I'm able to measure the masses of these 2. You know, order of magnitude. Don't answer if you already know, because you are working in a double beta decay experiment. They are extremely precise measurements, and the order of magnitude is 10 electron volt or something like this. So you know this this energy you know very, very well. And the dominating uncertainty comes from the energy resolution of with which you are able to measure the energy of the 2 electrons, but not from the position. And so coming back to what I was saying, you just need to see the neutrinoless double beta decay to claim that neutrino is a Majorana particle. The main point is that to claim that you see a double beta decay, you have really to check that the position in which you see this peak is exactly the position corresponding to the transition energy, because with this transition energy, I mean, you have a very narrow uncertainty coming from the nuclear measurements. So it's, in some way, the resolution, energy resolution of your detector is important in the identification of the signal. And then this is the 2 neutrino spectrum. And the endpoint is the same. So there are few events that are produced by this channel, but that populate this, I mean, the region corresponding also to the neutrinoless channel. And this is what we call in a irreducible background for neutrinoless double beta decay. Okay, what we call background in this field is any event that can mimic a neutrinoless double beta decay. So any event that in my final spectrum is here. And for sure, two neutrino double beta decay, when they happen with an energy that is high enough, are mixed with neutrinoless double beta decay. And so one of the point of how can I solve this problem? There are, I mean, it's a background that is there always. So what are the strategies that you can devise to get rid of this background? Have a good energy resolution, of course. And in this field, the good energy resolution is a resolution of the order of keV, so much higher than the uncertainties that I have here. But we have experiment with 300 keV energy resolutions. And the other is to study a decay where, I mean, an isotope where the two neutrino double beta decay is very long. Okay? If it is very long, you have less events here. This is a very good question, and you will ask to Luigi Coraggio. What I can tell you is that, okay, you know, there are phasions also in physics. So when I started working in neutrinoless double beta decay field, so I was as young as you, most of nuclear physicists, at least a group of them, was convinced that there was a clear relationship between two neutrino and neutrinoless double beta decay. Then nuclear physics has evolved, and now, I mean, the reason why they are not so correlated is that the way in which you really also, I mean, the way in which the nuclear process takes place is a bit different. But I think Luigi will answer to this question. So since there is not that correlation, it doesn't mean that I have to study a short-lived, I mean, an isotope with a short two neutrino double beta decay to have more chances to see neutrinoless double beta decay. Okay, this is not the case. So, I mean, in my list of the best and the worst candidate, among all the other considerations, that is the isotopic abundance, the Q value, and so on, I can add this on the half-life. And then, what is the other problem? The other problem is that I have a lot of other processes that can mimic a neutrinoless double beta decay, because, I mean, the signature is very nice because it's a monochromatic peak, but it's just the energy of, I mean, it's just an energy. I don't see any other, at least now. We are discussing only on energy. How many different sources do exist that can produce in my source equal detector signal in here at 2 MeV? They are really a lot. And so this exercise I want to do is to understand what these sources that here I have listed. They are for sure cosmic rays. Then I have environmental neutrons that are connected to cosmic rays, but we generally separate, their analysis. And then radioactive decays, mainly natural radioactivity. And so we have to analyze, if I have to choose a candidate, to choose a technology for my source equal detector experiment, and design my experiment, I have to understand how to get rid of these three sources. Shall we? What's when is the? This exercise will take also. Okay, I'm going ahead, and then we go on in the afternoon. Okay, so let's start. We try to analyze one source from the beginning, and then I will go faster on the other. Let's start with muons. Okay, the muons, or if you prefer, I say muons because the solution, the first solution that we have to adopt is to go underground, to be shielded from cosmic rays, and the only component of the cosmic rays that survives underground, if I exclude neutrinos, is muons. So the question we have to answer are how the source is produced, because in this way I understand how to reduce it, what's its energy spectrum, if underground I have advantages in going underground, what is the interaction of these particles in my source equal detector, which kind of interaction can mimic a double beta decay that will provide a signal in here, and if I can apply technique of active rejection or something like that. So muons or cosmic rays, they are produced, we have cosmic rays coming in the upper atmosphere. They are mainly, what is the major component of cosmic rays? Primary cosmic rays are protons. They start interacting at about 10 kilometer depth in the atmosphere. They produce mainly pions and kaons, this decay. And so this is a picture of their decay. And I get muons. Here you see the spectrum of muons at sea level. Is the flux versus energy. There are two plots. One is really the flux versus the energy, and the other is a way that maybe you have already seen in the field of cosmic rays in order to enhance particular structure in this spectrum. Often it is represented not as the flux, but the flux times the energy or the momentum at a power law of the energy of momentum. So I know exactly the flux of cosmic rays at sea level, but especially I know that they are too much for my experiment. This is a plot of that illustrates the muon flux reduction in the different underground laboratories. And the arrow point toward the Gran Sasso laboratory, where we have 2 big experiments that are Legend and Cuore running, for searching for double beta decay. And this is the flux over there. There is nearly a 6 order of magnitude reduction when I go deep underground. I still see muons, and the average energy is this one. So what is the interaction, what's the kind of interaction that I should expect from a muon with this energy? What happens when it enters my source? We generally use a word to label this kind of interaction. This is a particle. It can produce shower, but mainly ionization. Exactly. So I think I have a plot. This is a plot of the stopping power of muons. This is in copper. In the energy region that we are discussing in here, they are close to what we call the minimum ionization. So the muons mainly cross my source, and then they ionize the source in the path. They can also interact in a number of different ways, but for sure they ionize here. And so if you look at this number here, and you put numbers and you evaluate the stopping power, you discover that in this energy region, a muon more or less lose 3 MeV per centimeter square gram, and then you multiply by some density, and you get that your muon lose about 30 MeV in each centimeters. So it's much higher than our signal. So it would be some here, unless it crosses your source really close to the edge, okay? Because you see, my signal has an energy of 2 MeV, and this corresponds to a track, let's say 2 millimeters. And so if you want to mimic something like that, you need a muon that crosses really on the edge. Any other interaction of muons? Yes. There are a lot. Here you see a sketch where there are they are shown. You have ionization, pair production, Bremsstrahlung production, and then you also can have a nuclear inelastic scattering. And one kind of interaction that is particularly dangerous is when in some way muons produces neutrons and give rise to metastable nuclei. This is something similar to what happens when cosmic rays interacting in the atmosphere produce what we call cosmogenic radioisotopes. And because it may happen that there is a metastable nucleus that is produced and its decay gives rise to a signal in here. How can we get rid of these residual muons? I mean, once I'm down, I'm underground, what can I do? What can I do? It's a problem. Sorry, say it again. Yes, of course. I mean, the problem I have to get rid of muons that produce an event over there. Okay, all the others does not. So I have to. I need a veto because you see what we can call passive reduction is already achieved. So I installed my experiment in Gran Sasso. So maybe I can go to Snow Lab, that is deeper. It's not a very nice place, if I have to say. Much better at Gran Sasso. But besides that, but then even in Snow Lab, there are still some residual, much lower, but some residual muons. And so what I can do is to build a veto. So this is a very general description of a veto. Assume that I have a dome. My experiment is under the dome. All muons come from above, not from the Earth. You know, there are muons that come from downstairs in upward direction. They are produced by neutrinos. So if I see a muon from the center of the Earth, it is produced by a neutrino. But they are extremely rare, so that is not a problem. for the time being, it's not a problem. So since muons have this property that they lose continuously energy along their track, I can track them. And so I can have this dome made of an active material in which the energy the muon lose an amount of energy that is enough to get a signal. And this is often done, I mean, it can be done with a plastic scintillator, or in a lot of double beta decay experiment, this is done with not only double beta decay experiment, but also neutrino. It can be done with a Cherenkov detector or with a liquid scintillator. I mean, the point is that you need a big volume, because generally, I mean, this is big. And you generally do not have only the source. You have an infrastructure in which the source equal detector is hosted. So it's not, I mean, it's a building, or in any case, it's not a small infrastructure. Therefore, your veto needs to be quite large, and therefore you have to choose something that is affordable also from the point of view of the cost. And that is a good solution. The only case in which it could not be enough is when muons produce a neutron, the neutron activates a metastable nucleus, and then this metastable nucleus decay after a long time. Because you see the point. The point is that I tag, with my veto, I tag a muon. And then I tell to my data acquisition, pay attention, if you record a potential neutrinoless double beta decay event now, keep in mind that there was a muon in your muon veto. And so generally you discard that event because potentially it is induced by a muon. But I cannot tell to my data acquisition, okay, wait for two or 3 days or 2 or 3 years, because maybe you have produced a metal stable nucleus that we have to wait for to be sure that it has decayed. Okay, so first you need to understand exactly which are the metastable nuclei that are dangerous for your experiment, and then you have to devise a different way to get rid of their potential production. Okay, so muons are more or less the easy part of the problem. Not always easy, but in any case, at least you know them quite well. But it's not easy, on the other hand, to study metastable atoms that are produced by them. And also for a while, it was not also, I mean, often, for example, for the evaluation of how many neutrons are produced by muons, you have to rely on simulation. And you need to validate this simulation because, I mean, this is a field where also validation of simulation was not much developed because the needs of double beta decay experiment are so different from the needs of other experiment that sometimes I mean, you use tools that are not fully validated. So metastable states are not easily understood and validated experimentally from the experimental point of view. Okay, the other two sources are neutrons and radioactivity, but maybe we have lunch. And so you can think to the solution for these two sources over lunch, and we'll go back later.
Two small things. So one is, if some of you are not terribly familiar with all these interconnections, for example, how from a muon we generate a metastable nucleus, or what is a metastable nucleus, then at lunch you can pester Maura, just as much as you pester Claudia. The second thing is we have probably two options. One is, so we are about 1 hour late, which is okay, no worries, because we have very light afternoon. We thought we would have lunch at 12:30 and then resume at 2, so 1 hour and a half break. I can put it to a vote. Do we want to do a solid 1 hour and a half break and start at 3? Or do you want to reduce the lunch break and start, for example, at 2:30? What would you prefer?
No, for me it's the same. I mean, the point is, I can go faster, or if you prefer to go ahead with this kind of question and answer, you may reconvene at 2:30.
Midway, 2:45. Okay, let there be a 1 hour and 15-minute break. We reconvene at 2:45 with continuing talking in this interactive way on how to construct. Oh, this is the question I don't